So we're going to talk about organic structure determination. And here's a couple of problems. You can think back years ago, many years ago, it must have been very difficult to determine organic structure. And the way they used to do it was just by doing reactions on pieces of molecules. So they would take molecules and they would rip them apart and then try to build them back. And by the reactions that they would use, they would infer structural aspects on the molecules. This is quinine. It's used to battle malaria. It's also found in tonic water. It's fluorescent. If you ever put tonic water on a black light, you'll notice that it fluoresces. It took 54 years after its discovery to determine its structure. 54 years of work. Penicillin, discovered by Fleming, took a long time, and not only that, these three people all won Nobel Prizes for various aspects of chemistry. These two very famous organic chemists, this lady was an X-ray crystallographer. The organic chemists actually got it wrong in determining the structure. It took many years. These were the structures they proposed. This is the actual structure of penicillin, and it was determined using X-ray crystallography. I think it was in the 40s, late 40s. It took several, I think a little over a dozen years to determine the structure of penicillin. This is the 3D structure of penicillin. Since that time, there's been a new instrument developed called the nuclear magnetic resonance spectrometer. We're going to talk about that mostly on Friday, but we'll introduce it today. But how do we go about determining these structures? And that's one of the things you may have been wondering. We do all these reactions. How do we know that's the real structure? And that's a key element of working in the lab. Now, one of the things that's interesting, we'll do these different structural determination problems. You do have to remember that when you work in the lab, there are chemists we call natural products chemists who go out and they find and isolate chemicals from plant material, from sea animals and shellfish that have medicinal properties, and they find these molecules and they have to determine the structure from scratch. You should remember that when we're determining structure, most of the time it's from a chemical reaction where we took the starting materials, so we actually have some idea. Most of the time when we're doing structure determination, we're actually doing structure confirmation. So when we work in the lab and we take molecule A and molecule B and we do some reaction that just couples them, we have a pretty good lead on what the structure should be, given our starting materials and the reactions that we used. And that actually helps us when we get back to determining the structure of unknown compounds. So the first thing we do is figure out what the molecular formula is. And in the past, quantitative chemical analysis, we did this. I forgot to get rid of all the animations. I apologize. We don't need it. We measure, what we typically would do is take our compound and burn it, and then we can absorb all of the water that comes off in magnesium perchlorate. We can absorb all of the CO2 with sodium hydroxide. It has a tendency to pick these things up, and we can tell how much CO2 and H2O comes off, and we do an analysis. And that works for carbons with just carbon, hydrogen, and oxygen. There's other ways to find other things. Okay, so what this gives us, though, is just an elemental composition. So for instance, we might burn an organic compound that just has carbon, hydrogen, and oxygen, and this is what we get. So these are problems you've done. How many people think they could get the empirical formula from this now? What would you do? Most of you could. The easiest way to do this is to say, well, let's just assume I have 100 grams of material. And if I had 100 grams of material, it would contain 64 grams of carbon, 10.8 grams of hydrogen, and 24.6 grams of oxygen. We will then convert that to moles. We just divide the mass by the molar mass, or of the atomic mass, rather, of each of those elements. And we get something that we can call an empirical formula, and that is C5.38, H10.7, O1.54. That doesn't look like any molecule I know of. So what we will do is take the lowest coefficient and divide each of them by that. That gives us 1. Now notice we have C3.49, H6.95, and O1. Still doesn't make sense, but that's very close to this, right? We're going to be off a little bit because of experimental error. We cannot have half a carbon atom, so we're just going to double this, and our empirical formula then becomes C7H14O2. It's that easy. These problems, one of the things you want to remember when you get these problems is just assume you have 100 grams, break it down into this, divide by the atomic masses. That will give you something that looks like this. Divide by that lowest coefficient, and then you may have to multiply it. The question most students ask is, how do we know, like 3.49, we rounded to 3.5, 6.95, we rounded to 7. You have to have some idea as to the experimental error. And typically, the experimental error in these types of experiments is enough that if that were 3.4, you're getting close to the experimental error. So typically, the number you have to multiply this by should be 2, 3, 4, at most 5. To get to something like this, okay? So you wouldn't multiply by 9 or 10 because then you're outside the realm of experimental error. So you can round up from 3.9s, you can round to 4. 3.8, I would, that's probably a real number. One of the things that is important in organic chemistry, hopefully we remember that for hydrocarbons, for alkanes, what's the molecular formula for an alkane? Well, the generic one is CNH. Anybody remember how many H's are in an alkane from last semester? There's some function of N. Is it 2N, 5N? 2N plus 2, right? So that we call that's saturated. Okay, we have nothing but carbon-carbon and carbon-hydrogen bonds, and there's no ring, okay? So, for instance, 1, 2, 3, 4, 5, hexane is C6H14. As soon as I make cyclohexane, can anybody tell me the empirical formula, or the molecular formula for cyclohexane? C6H12. It has 2 less hydrogen. So we talk about an unsaturation index. That tells us how many hydrogen are missing. Sometimes you'll hear it called the index of hydrogen deficiency, or IHD. So we can easily determine this number from this. If we have C10H18, how many hydrogens are missing from a saturated hydrocarbon? A saturated hydrocarbon would be C10H22. So we say this has an unsaturation index of 2. It's missing 4 hydrogens, but a double bond accounts for an unsaturation index of 1. Every 2 hydrogens accounts for an unsaturation index of 1. So if we're missing 4, the unsaturation index will be 2. A ring accounts for 1. A double bond accounts for 1. Every pi bond counts for 1. So if we have a triple bond, it's 2. And there's a formula you can use. You'll find various forms of this thing, but typically the unsaturation index equals 2C plus 2 plus N minus X, all of that divided by 2, where C is just your number of carbons. We could actually throw silicons there. It's actually the number of all of your tetravalent atoms. N is the number of your trivalent atoms, and X is the number of hydrogen and halogens, your monovalent atoms. And that will give you the saturation index. What does the saturation index tell you? If I have a saturation index of 1, it means I either have a pi bond or a ring. If I have a unsaturation index of 2, that tells me I either have 2 rings, 2 pi bonds, or a pi bond and a ring. It's telling me that there's some missing hydrogens. And that's important. That's one of the things you should start with when you're trying to determine an unknown structure. Right away, if you have a C6 compound with an unsaturation index of 1, you know either it has a double bond or it has a ring. And that really simplifies determining the structure. So you can try this for each of these using that formula. I won't bother today because I want to get your test back. Another way of getting a molecular mass for a compound is something called mass spectrometry. Have you guys been exposed to mass spectrometry? Maybe a little bit. So we're not going to go into this in great detail. But in a mass spectrometer, we take a molecule, we put it under very, very low pressure so that it goes into the gas phase quite easily, and then we bombard it with high-energy electrons, 70 electron volts or so, somewhere around there. That's a lot of energy, 1,600 kcals per mole. If we had a mole of electrons, that's the value. Notice that's enough energy to start breaking bonds and everything. What happens, our molecule gets hit by a high-energy electron, and it just knocks an electron out, and our molecule now is missing an electron. At the instant that happens, nothing else happens. One of the things you want to think about with mass spectrometry is remember that molecules are better described by molecular orbital theory, so you can knock an electron out, and it doesn't necessarily have to be localized in any one bond. It can be over the whole molecule. As it turns out, there's instances like if we have heteroatoms, there's some orbitals that are very localized, and there's other orbitals that are very diffuse where the electrons are all over the molecule. So when we knock it out, we have this thing we call it the molecular ion. Notice that we have dot N+. It's a radical cation. It's both a cation and it's a radical. Most of organic molecules, the vast majority, there's very few exceptions, have all of the electrons in them with paired spins. They have an even number of electrons, and the spins are all paired. When we put them in, if we were able to figure out all the orbital energy levels, we would have 2 electrons in every filled orbital. And every orbital that had electrons in it would have 2, so they would be paired. When we knock an electron out, we have one orbital, at least one orbital that has a singly occupied electron. So it's missing that minus charge of the electron. That's what makes the neutral molecule. It loses a minus charge, and it becomes positively charged. That's what makes it a cation. And we have now an odd number of electrons, so one electron must have unpaired spin. It's a radical cation. So here's an example. We can take propane, put it in a mass spectrometer, hit it with a high-energy electron, and it knocks an electron out. So notice we had one electron. It hits this molecule, knocks it out. We have 2 electrons, and the other thing we have is a radical cation. We have something with a positive charge. What that enables us to do, this is a schematic diagram for a mass spectrometer. This is the chamber where we ionize everything, and then we heat it up so it can vaporize. We hit it with an electron beam. That gives us a radical cation. It has something with charge. We then put it through a high electric field that propels it very fast. This is all under vacuum, too. So it goes through this electric field, and it shoots out of here at a high velocity, and then it enters a magnet. And the magnet will cause the positively charged compounds to turn left in this case, okay? How much they turn left is going to be a function of their mass to charge ratio. If we had knocked 2 electrons out, their mass to charge ratio is greater. Almost all the molecules will only have 1 electron knocked out. It will turn, and how much it turns depends on its mass to charge ratio. So when it hits the detector, the lighter ions will have turned further left. than the heavier ions. And we can then detect the mass. We can calibrate that. Our lighter ions will hit on this side, and our heavier ions will hit over here, and we can just get a spectrum from that. We'll see what a spectrum looks like in just a second. So that's how a mass spectrometer works. This is a mass spectrum. Here's a mass spectrum of propane. If anybody did a quick calculation, the molecular mass of propane is 44, and we see a peak right here at what this is. On this axis, we have our mass to charge ratio, and we know that the charge on almost everything that we're interested in has +1. So our mass to charge ratio is equivalent to the mass. We have a peak there at 44. What else do we see here? On this scale is our ion count. We typically see mass spectrum where we talk about relative abundance. So what we do is we take the biggest peak and divide everything by that number so that this number becomes 100%. Okay? So that is our most abundant ion. This thing D, we talk about that. In this case, that's our molecular ion. That is, it's propane with just one electron knocked out, mass of 44, and we see it. We don't always see our molecular ion. Quite often, we don't, and we'll talk about that in just a second. What else do we see in these things? Well, one of the things we see is a lot of different peaks. Why do we have all of these different peaks? Well, if you think about it, we've just knocked an electron out, high energy, 1,600 kcals per mole. That's enough to break bonds. Those radical cations are very unhappy species, and they break apart into more stable compounds. Some of those things will be charged, and if they are charged, positively charged, we will get a hit on our detector from those positively charged things. The things that are neutral, we don't see. They just run into the side of the mass spectrometer. They don't make the turn. Okay? They don't turn left when they hit the magnetic field. We also see a lot of small peaks. Now, what's going on here? We'll talk about this in a second. One of the things you have to remember is that carbon, for instance, what's the atomic mass of carbon? Well, atomic mass is defined as carbon-12 has an atomic mass of 12. But there's also carbon-13. It's an isotope of carbon, and it has atomic mass of different than 12 because it has an extra neutron in its nucleus. It has an atomic mass of 13. There's also carbon-14, and there's carbon-11, and all of these different isotopes have different abundances. The same with hydrogen. Most hydrogen has an atomic mass of 1, but some hydrogen has an atomic mass of 2. We call that deuterium. Most hydrogen has just a proton and an electron spinning around it. But some hydrogens have a nucleus that contains a proton and a neutron, so it has an atomic mass of 2. So that's why we see a little peak out here that's 45. Those are molecules of propane that have either a C13 or a deuterium in them. Will give us that, okay? So we see this isotopic distribution. But we've already seen that these things can fragment. So that molecular ion is an unhappy species, has a lot of surplus energy. It can fragment to give specific ions, and these ions are diagnostic for particular compounds. What happens is they can break apart. There's our parent molecular ion, and it can break apart. This one is easy. It can really only break into two things. We don't very often cleave carbon-hydrogen bonds, but we very often will cleave carbon-carbon bonds. And when we cleave a carbon-carbon bond, it's going to give us a cation and a radical. There's two possibilities in this instance. We could get the ethyl cation and the methyl radical, or the ethyl radical and the methyl cation. Which one, when it breaks apart, the electron stays with one component and the other one becomes electron deficient. We will only see the positively charged thing in our mass spectrum. So if we go back to this spectrum, notice that we have large peak at 44, and then we have another peak at 44 minus 15 at 29. Okay? We don't see a large peak at 44 minus 29. We see a little peak out there at 15. Okay? So this peak is due to the ethyl cation, and this peak is due to the methyl cation. Notice that the peak for the ethyl cation is much larger. Why is that? Well, as it turns out, we know that radical stability is a reflection of carbocation stability. But in terms of stability, it's much more important for the cation to be stabilized versus the radical. Radicals aren't as unhappy as cations are. So in this instance where we get the ethyl radical and the ethyl cation and the methyl radical, that's more likely than this case where we have a methyl cation. Methyl cations are really, really hard to make. We can make them in a mass spectrometer, but we'd much sooner have an ethyl cation. So the cation stability is the most important aspect, and the radical stability that comes off is the second important aspect. We call these fragmented cations daughter ions. So if we take a look at octane, here's a look at octane. Now we have an opportunity to break a lot of different carbon-carbon bonds, get a lot of different fragments. What we see, this is actually a simulated spectrum, and it's not a very good one, because we would see there's our parent molecular ion. That's the molecular mass of octane. And we see a large peak where we've cleaved this bond from the radical cation. We've lost an ethyl radical to form that cation. And then we can see we broke that bond, we could break this bond or this bond, and we see those peaks as well. We don't see a large peak where we break one of the terminal bonds, and that's because we'd have to make a primary radical and, a methyl radical and a primary carbocation. If we break this one, we get a primary radical and primary carbocation. So it's a lot easier to break one of these internal bonds and not that one on the end. As it turns out, we actually would see a little bit. Here's hexane. This is a real mass spectrum. There's the parent ion. Notice that we see a small peak at the M plus one. That's because of either C13 or deuterium that's present. We always see a little bit there. And then we can see a small peak where we've cleaved this bond, but the largest peak is where we cleave either this bond or this bond, okay? And then these get progressively smaller. And this is just a statistical distribution because the bond strength for each of these internal bonds is about the same, but it's just that we can break this bond or this bond to see this fragment. So we get a lot larger peak for that. So when a molecular ion fragments, it will yield a neutral radical, which is not detected, and a carbocation, which is detected because it has an even number of electrons and it has charge, so we can see it. The fragmentation will be dictated by the more stable carbocation as well as the more stable neutral radical. And I just want to give you an example here. Here's an example where we can actually get some different fragmentation patterns. So this is 2-methylbutane. When we knock the electron out, this is our molecular ion. And then that molecular ion can fragment, and it can break this bond to give this secondary carbocation and this methyl radical. Or it can break this bond to give this secondary carbocation and this ethyl radical. So in terms of the stability, both of these are secondary carbocations. They should be fairly similar in their stability. So we might expect to see more or less equal amounts of these fragments. However, in this case, we form a methyl radical that's much less stable than an ethyl radical. So we would expect, this is less stable than this. This is the most stable radical. we would expect that to be the base peak. And as it turns out, when we take a look at the spectrum of this, we will see that as the base peak, 43. That is this fragment with a positive charge on it. That's the most popular bond to break. Notice we do see a significant amount of the M plus minus 15. Okay? So these are very diagnostic, and we can tell molecules that have the same molecular formula. So let's take a look at these two molecules. Here's the mass spectrum of these two molecules. Notice they look pretty similar. They have a lot of peaks in common, but this one has a significantly larger peak here. But more interesting, this one has a very large peak for loss of 15. 15 is a methyl group. Okay, if we lose a methyl group, we lose 15 mass units. We have a large peak there. This one does not have loss of a methyl group. So if we take a look at these two things, if we cleave a methyl radical off of the radical cation, we have to form a methyl radical and a primary carbocation. But if we cleave this methyl radical off, or this one actually, we have a radical come off and we form a secondary carbocation. So we expect that this might be a fairly stable peak, and indeed that is. This is the mass spectrum for this compound, and that's how we can tell the difference between these two, because we have an opportunity to form a secondary carbocation with this one. In this one, we don't have an opportunity to form a secondary carbocation. So we talked a little bit about isotopic distributions. So here is a mass spectrum for methane. Rather boring. Methane has a molecular mass of 16, and we see a little bit here at 17. That's because of mostly carbon-13 and or deuterium. However, deuterium is a very, very low abundance, so most of this peak is probably going to be attributed to methane molecules that have a C13 in them. 1.07% of all methane molecules should have a C13 atom in them. And this is the isotopic distribution, and it can be very diagnostic. Most of the time it's hard. You'd have to look and take a look at the ratios of this, and it's somewhere around 99 to 1, close to that. That's what we would expect. But take a look at chlorine and bromine. They actually have significant amounts of another isotope. So most chlorine is chlorine 35, 75%, slightly better than 75%, but almost 25% of chlorine is chlorine 37. So we would expect to see a significant, what we would call M plus 2. So that's the parent radical cation plus 2 atomic mass units because of this isotope. And for bromine, we expect to see that the 79, the peak due to whatever bromine has 79 and whatever has 81 to be about the same. So let's take a look at, here is chlorobenzene put through a mass spectrometer, and what we see out here, here's our molecular ion. We have a very significant peak, about 25% as high as our base peak. That is due to having that chlorine 37 in it. So that's very diagnostic. Notice now, we can also tell that all of these fragments below, this fragment is due to just loss of the chlorine atom because we no longer see that isotopic distribution down here. It's gone. That means that the chlorine's gone in these fragments. If we take a look at bromobenzene, we might expect a similar spectrum. And take a look from 80 down below, and those spectra look very much similar. And here we see the parent ion. But notice that this is nowhere near as large as it was for the chlorine. It's nowhere near In fact, the base peak for chlorobenzene is the parent molecular ion. But the base peak for this compound, oh, I'm sorry, I made a mistake. This is benzyl bromide, and this is chlorobenzene. So that explains this even more. So why do we have such a small peak for here? And notice our parent peak is at about 93. Why is that so small? Well, it's because we can cleave off the bromine very easily. So it's no longer, this is a very weak bond. This bromine to benzylic carbon is very weak. Benzyl cations are very stable because they can be resonance stabilized. So this is a very weak bond, and this no longer is the parent ion. So from mass spec, all we get is a molecular mass. How do we convert that into a molecular formula? I put a little video of this because I want to get your exams out. Put a little video about the rule of 13. Okay, so one of the things you're going to have to do, how many people can divide by 13 without a calculator? You might want to either bring your calculator or practice, but this is actually quite easy because we go old school division here, because what's important is how we divide we get a molecular ion that gives us a molar mass. We divide it by 13. 92 divided by 13 is 7. The important thing here is not the decimal, but the remainder. How many people remember what a remainder is? It's actually surprising. Some people don't remember what a remainder is. Remainder is that bit of number that's smaller than 13 when we divide 92 by 13. In this case, it's 1. So the reason we use 13 is because that's the mass for a CH unit. And so when we divide our number by 13, we're just assuming that we have that many carbons and that many hydrogens. The remainder now, 1, tells us that we have one more hydrogen at least. In this case, our molar mass of 92 could be accounted for by C7H8. So that's our candidate formula. We can now evaluate for alternative candidates by replacing. So for instance, it's C7H8, but what if we said, what if there's oxygen in there? Well, if we put oxygen in, we have to take a C and 4 hydrogens out. Why? Oxygen has an atomic mass of 16. This fragment has a mass of 16. So if we put an oxygen in, we'd have to pull off 1 carbon and 4 hydrogens, so our compound could be C6H4O. Okay? These are things you'll have to remember. A nitrogen, if you want to put a nitrogen in, you have to pull a carbon and 2 hydrogens out of your formula for every nitrogen in there. And these are the different substitutions. I will tell you, I'm not going to give you a big complicated question like this on the exam or quizzes. I will give you carbon, hydrogen, maybe oxygen, nitrogen, nothing else, okay? So do some practice. There's a little video in the Acorn site. It's not my video, but just from YouTube on using the rule of 13. So give that a look. The nitrogen rule is another rule, and it's a simple rule. Compounds containing an odd number of nitrogen have an odd mass number. So if you just have a hydrocarbon or a hydrocarbon with oxygen, it will always have an even mass number. If you have 1 nitrogen, you'll have an odd mass number. If you have 3 nitrogens, it'll be odd. If you have 2 nitrogens, it'll be even. Why? What's the molar mass of nitrogen? Well, it's 15, right? So if you have 2 nitrogens, you have 30. So hence the nitrogen rule. So if you have an odd number right away, you know there's probably nitrogen in there. And again, you can have other things. You might have phosphorus, chlorine, these other things. But barring that, I won't give you anything in terms of determining a mass that have anything but carbon, hydrogen, oxygen, and nitrogen. Take a look. You can calculate the unsaturated index just by looking at this. What is the index of hydrogen deficiency, or the unsaturation index for this molecule? How many people can figure it out now? How many double bonds do we have? 3. How many rings? 1. So this one is 4. This one? 4. This one? It's not 4 because we have a nitrogen, oxygen. We'd have to draw all that, so it's going to be different from 4. And that's it. The next thing we're going to talk about, the last thing we're going to talk about, is nuclear magnetic resonance spectroscopy. You guys have been exposed to carbon. Notice this is a very complicated NMR spectrum. We have a carbon-13 NMR and a proton NMR. The only reason I put it up, it's actually a very beautiful spectrum. Usually these things are much messier, but we have very clear signals. One of the things you want to remember is if we focused in on these, we'd see that that might look like more than one signal. It's a multiplet. It's actually only one signal. So what NMR can tell us is it can give us quite a lot of information. It can tell us the symmetry of the molecule, which you can get from C13 and proton as well. But it also then tells us about the connectivity of the molecule. And the hydrogen gets a little bit more complicated because we end up getting these peaks that aren't single peaks. They're multiplets, but that gives us a lot of information. And we'll talk about that on Friday. So that's it. I have quizzes to pass back.